Welcome to the ORCA 6 release event, also from my side. I'm very happy to be able to tell you today about the new features that we have in ORCA 6 that enable us to simulate real-world chemistry. My name is Christoph Riplinger, and I'm the Managing Director of FACCTs. FACCTs is a spin-off of the MPI for Conformers, where the main part of the ORCA development is taking place. FACCTs is the abbreviation for Fast and Accurate Computational Chemistry Tools, and our mission is to bring exactly that to industry. So we are ORCA's link to industry users. Behind ORCA, there is the core development team, which is distributed amongst the MPI for Grundforschung, where the main part of the academic development is taking place. This is headed by Frank Niese, who's not just director and department head and founder of ORCA, but he's also a co-founder of FACCTs. At FACCTs, we are now about 15 people working also closely with our industry partners in order to make ORCA ready and accessible for industry users. FACCTs and the MPI are closely located. FACCTs is based in Cologne, and we are about a 1-hour train ride away from Mülheim. And that allows us also to have a close collaboration. And in the last 3 years, we worked together intensely to bring ORCA to a new level, to rework the entire backend and architecture of ORCA and make it ready for the future. And especially in the last year, in the last 6 months to a year, we worked very intensely to bring ORCA 6, to bring the ORCA 6 release to the finish line. I'm very happy that we have achieved this today. On top of that, we have a large group of academic collaboration partners around the globe. And on the following slides, I will show a few of the features that I will show are developed and implemented together with these collaboration partners. Just an overview, ORCA is growing quite tremendously. In the last years, we have a growth rate of about 25% per year, now more than 70,000 registered users. On the industry side, we have a lot of users from pharma, biotech, chemical industry, material science, and so on. Now to the actual topic, real-world chemistry applications. That's at the core of our heart. And that's not just important for industry, but also, of course, for a lot of people in academia, and not just protein ligand complexes for pharma, but there's a lot of other systems that are of interest, like drug molecules get larger and larger, material science molecules get larger and larger, and we also, the more capable our software gets, the more the demand also grows for more complex setups. And so also nowadays, it's also possible to model explicitly solvated systems at a very accurate level of theory. And so this is something that we try to push, that is at the core of our heart, as I said, and we want to treat real-world chemistry, and to be able to achieve that, there's a lot of different factors that need to be taken into account. And I will try to show you how we tackle these different aspects here with ORCA 6, how we are able to tackle these with ORCA 6. So the first part is efficiency. To treat real-world chemistry systems, we need to get faster, because then we can treat more systems at the same time. We can treat entire conformational ensembles, and we also want to treat larger and larger systems. And so with the help of the rewrite of our architecture, we were able to speed up DFT from GGA to hybrid DFT by more than a factor of 2 for a system like this of about 90 atoms. So when you compare the timings, ORCA 5 to ORCA 6, we have a speed up of more than a factor of 2, which is quite astonishing. Now, what does that give us? That gives us, if we look at a smaller system like this, a drug-like molecule, that gives us timings like a few seconds or a minute for very decent density functionals. If you want to go to couple cluster values, then you can also spend a little bit more time, 10 minutes, and you get a very good post-Hartree-Fock result, couple cluster result. And we can go to larger systems like this one with about 500 atoms and representative timing here, omega mean and 7 MV, 1.5 hours for this entire system. Now, if you are just interested in a small part of that system here, you can use our multi-scale simulations, and that way you can reduce the time by more than a factor of 10. Now, we managed to push the boundaries to bring down the memory requirements for and to tackle really large systems like this protein here. So almost 3,000 atoms with implicit solvation. We can now do these calculations in just a few hours on decent machines. Now, another important aspect, not just for industry users, also for academic users, is robustness. So nobody wants to repeat their calculations just because the SCF didn't converge. And so what we did also was, when going from ORCA 5 to ORCA 6, we also reworked the convergence. We spent a lot of time in making convergence better. And I had a slide for this prepared, but actually I got an email yesterday from a client who had access to a pre-release version, and I just wanted to let this quote speak for itself. So that guy, he's working on very complicated electronic structures, lanthanide complexes, and he sees that his calculations are converging much faster, about an order of magnitude faster. So this is very good. This is a huge step forward here. Another important aspect is robustness in terms of geometry optimizations. We were always getting good feedback about the ORCA optimizer. It's converging smoothly, getting good structures. But about 2 years ago, we had an evaluation from a pharma partner where they showed us data. They showed us their results, which were kind of disappointing to us. So for what they did, they had a large set of diverse structures, 50 different molecules, drug molecules, charged, neutral, and so on. And they had another software that I don't want to mention here what that software is, but they compared that software to ORCA 5. And what they found for regular DFT, they've always found minimum structures with both softwares, which was as we expected. But when they computed and verified the nature of the minimum structures using MO62X, they found that with that other software, everything could be optimized, but they found for 2 of the systems, they found small imaginary modes. With ORCA, this was the case for seven systems. So this was very disappointing for us, because that's not what we wanted to have. We wanted to be the best in the game. And so we reworked, I think that was an effort of about half a year. We reworked the optimizer, the entire scheme. And now with ORCA 6, we have a much more robust optimizer. So we have 0 imaginary frequencies here, also using MO62X, and yeah, mission accomplished. So robustness is key for us. We don't want to repeat calculations. We don't want to need to troubleshoot. We want to get a result with every single calculation, a meaningful result. Another aspect, real-world chemistry is usually happening in Solvation. And so an important aspect or an important feature are implicit Solvation models. We used to have, or we have, CPCM and SND models, and with ORCA 6, we wanted to also go beyond and include newer Solvation models, more sophisticated Solvation methods. And I just want to refer to Mikhail's talk. He will talk tomorrow about new Solvation features in ORCA. Another aspect for Solvation is explicit Solvation or micro Solvation. So you get much better properties for specific molecules if you saturate certain functional groups with explicit Solvation molecules. And for this, we have now a so-called micro solvator module within ORCA available. Also here, there will be a talk by Anneke in about half an hour. She will talk about ORCA's new explicit solvator. The next important aspect is, if you look at real-world chemistry, or at any chemistry, you need, in order to get a result that is compatible with the experiment, you need to work on the low energy or lowest energy conformers for single structures, but also for complex structures, for aggregates, when you have like 2 molecules binding together or 3 molecules. And for this, we have now a tool within ORCA available, which we call the Docker, which gives you accurate docked structures. So what you put in is 2 different structures, and our Docker puts them together in and gives you like the low energy interaction sites. And this can be used for various applications. There will be another talk later on, which gives you more details about this. For single molecules, but also for these complex structures, it is important to get the lowest energy conformers and to get a good conformer ensemble. And for this, we now have also a module available within ORCA, and that's the GOAT module. The expert himself will talk about this. So Bernardo, he developed and implemented the GOAT module and the Docker, and he will talk after my talk about conformational searches and the Docker and also other aspects, Delta SCF for excited states. And yeah, you will hear from him about how this works, and we'll also see a few nice examples from him. Now, chemistry, for real-world chemistry, reactions are important. And here we had, with ORCA 5, we had released our first version of the nudged elastic band method, which you can use to study reaction and to predict reaction mechanisms and to easily get transition states. And this was done in a collaboration together with the group of Hannes Jönsson from Iceland. Since the ORCA 5 release, there were a lot of people using that method, and we are getting good feedback about it, but also there were a few borderline cases, complicated cases where we saw that we need to improve the method, and that's what we've done with ORCA 6 now. So we have better initial path also for more complicated systems where we have large rotation of large groups, like you see here in this example. Also, if you have very separated reactants, then and they are coming together, forming a transition state and reacting to a product. Also, for these cases, we get better results now. Also, what we implemented is an excited state NUB method, which is now working quite nicely. So please try it out. When we don't want to look at a single reaction, but we want to find out, okay, how do two molecules react with each other? We have also a new module here. So the GOAT module that Bernardo will talk about also includes an extension that we call GOAT React. And that is a module to do reaction exploration. Essentially, what you do there, you put two or multiple molecules together, and GOAT React gives you the reactomer, so all possible reaction outcomes. I don't want to go into detail here, I just want to show you that we have now a nice tool chain to study such reactions. You can use for a molecule GOAT to find a global minimum. You can use the Docker to dock, for example, singlet oxygen to that molecule, and then you could use GOAT React to explore what reactions can happen between those two molecules. And yeah, this is just an example here. So for the reaction of singlet oxygen with this molecule, you get like a variety of different outcomes. And so you can study how a molecule, for example, is degrading when oxygen is present. Now, a few other features that I want to mention or want to highlight, there is quite some improvements on the local energy decomposition scheme, which we use, for example, quite a lot for protein-ligand interactions. Giovanni Bistoni will talk about this tomorrow. Another aspect is our new plug-in method for external potentials. So in the last years, there was a lot of progress on the machine learning side. There's quite a few interesting machine learning potentials being developed by the community. And we did not do the effort to include any of these machine learning potentials into ORCA, but what we do is to allow to plug in external machine learning potentials into ORCA via scripts. And that way, we can use all kinds of nice methods that we have within ORCA, like optimizations, constraint optimizations, scans, frequencies, NEB, GOAT, and so on, also with machine learning potentials. We have a repository that's called ORCA Quantum Chemistry. We used to only store our compound scripts there. Now we also have another part that is called ORCA External Tools. And here we provide a few plug-in scripts that you can use to plug in different machine learning potentials. And we also encourage you to either you have an own machine learning potential or you want to use some machine learning potential. If there's no script available, please develop those scripts, and via pull requests, we will be happy to also include those in the repository. On the documentation side, so now we're done with all the new features on the documentation side. There's quite some important addition to ORCA. So we have now a citation tool within ORCA available, which prints you out at the very end of an ORCA calculation what papers should be cited in a manuscript that makes use of this specific calculation. And this helps you to be compliant with good scientific practice, with citing the papers that or the references that were used for your calculation. And for your convenience, we also provide, or every single ORCA run provides, a BibTeX file that you can use to integrate those citations. We also extended our tutorials for these new features. You can find them on the FACCTs homepage under documentation. And I'm very happy about this. We now also have an online manual available. There were a lot of requests from our users to not just have the PDF manual, but also have an online version of the manual. And this will now be published today. You can see it here under the FACCTs homepage documentation. ORCA, there's now for ORCA 6, there's now a manual available, and it has all the nice features that online manuals usually have. Hyperlinks, cross-referencing, easy search functionality, and so on. I want to finish here with thanking our partners. So first, I want to thank the FACCTs team. It's a lot of fun to work together. Then our partners at the MPI. It was a tremendous effort to get ORCA 6 out, and I'm very grateful for the good work that we've done here together. I want to thank our collaborators in the Grimmett group for a lot of important contributions to ORCA. Also, the newer Solvation models for XDB, for the DFT developments, and I'm very happy that we have a very good exchange. So we are not just close to Mülheim, but we're also close to Bonn. So Cologne FACCTs is like half an hour train ride apart from Bonn, and we have frequent exchange, frequent visitors from there, and there's quite some good exchange with the Bonn people. I also want to thank the Bistoni group, who's taking care of the LED development, the Hannes Jonsson group in Iceland, who's taking care of the NEB development, and Simon Müller and his group in Hamburg, who's developing the Open CosmOS tool and helping us with the integration into ORCA. I want to thank you for listening, and now I wish you to have fun using our ORCA 6. I'm here to answer any questions you might have. Thank you very much.